Okay, let's unpack this. You know how sometimes you stumble upon a connection between things you thought were totally separate?
Mm-hmm.
Prepare for something? Well, pretty mind-bending. We found this discovery where the strange rules of the quantum world pop up in something as tangible as a magnetic material.
Yeah, it's really fascinating stuff.
So we're diving deep into a recently observed phenomenon. It's got a name that might sound like science fiction.
Yeah.
The Magnonic Dicke superradiant phase transition.
Exactly. And we've spent time really getting into the details of the scientific paper and its supplementary info that describe this observation. It's quite remarkable.
Right.
Think of this deep dive as maybe your shortcut to understanding a piece of pretty cutting-edge physics.
Good way to put it.
Our mission really is to clarify what this phase transition is all about, why it's generating excitement, in the scientific community, and maybe what it reveals about how matter fundamentally behaves.
Aiming for those aha moments.
That's the goal, yeah, where complex ideas suddenly click.
Absolutely. So let's break down that name. It's quite a mouthful.
Yeah.
Starting with Dicke superradiance.
Okay.
When you hear superradiance, it just sounds big, extraordinary, right?
It does. And the concept, it actually goes way back. It has its roots in a model from the 1950s by Robert Dicke.
Okay.
So imagine a collection of tiny energy emitters. Originally, he was thinking about atoms interacting with light.
Right. Atoms and photons.
Exactly. Normally, these atoms, they'd emit light independently, kind of random, unsynchronized.
And doing their own thing.
Pretty much. But under specific conditions, they can start to cooperate. They essentially act together, like a single giant emitter.
Huh. So instead of lots of little weak flickers of light, you get one incredibly strong coordinated burst.
Precisely. This cooperative behavior, it leads to a much more intense and rapid release of energy than you'd expect just by adding up all the individual atoms.
Right.
That's the core idea of superradiance. Now, the superradiant phase transition, or SRPT, that takes it a step further.
Okay, what's the transition part?
It describes a critical point. A point where the entire system just abruptly shifts into this collective superradiant state. And that happens once the strength of the interaction, between the emitters and the field around them hits a certain threshold.
So it's like flipping a switch.
Yeah, exactly. Like a switch flipping from individual action to complete synchronization.
Okay, so flip the switch, go from normal, independent behavior to this synchronized, superpowered emission.
Mm-hmm.
And in Dicke's original model, this switch flips when the energy of the emitters perfectly matches the light's energy, what they call zero detuning.
That's right. Zero detuning, like two perfectly tuned instruments resonating together.
Okay.
Now, here's where it gets really interesting for this research we're unpacking.
Yeah.
Because it isn't about atoms and light in that traditional sense. Instead, the emitters, well, they're magnons.
Magnons. Okay, quick refresher maybe. What exactly are magnons?
Right. Think of magnons as collective sort of wave-like disturbances of electron spins inside a magnetic material.
Okay.
Yeah, imagine the atoms in a magnet, right? Each atom has this tiny internal compass needle that's the electron spin.
Got it.
A magnon is like when a ripple travels across a pond, but instead of water molecules, it's these tiny compass needles, the spins, all wobbling together in a coordinated way.
Ah, like a wave of wobbling spin.
Exactly, passing this wobble along to their neighbors. So this research, and it builds on some earlier work too, it demonstrates that these magnons in a solid material, specifically this stuff called erbium orthoferrate, or FeO3.
FeO3, okay.
They can also undergo a Dicke-like superradiant phase transition.
So magnetic excitations acting together instead of atoms emitting light.
That's the key takeaway, these magnetic excitations acting in a synchronized way.
That's a really fascinating shift.
Yeah.
So how did they actually observe this magnonic superradiance? What was the evidence?
Well, the paper goes into quite a bit of detail on the key experimental observations. One really crucial piece of evidence comes from looking at how terahertz radiation...
Terahertz, okay. Like light, but lower frequency.
Exactly, a type of electromagnetic wave. They looked at how it interacts with the material when you apply a magnetic field, and they observed something called an anti-crossing behavior.
Anti-crossing. In the frequencies of polaritons, right?
You got it, polaritons.
Those are the hybrid things, light and matter mixed together.
Perfect. Yeah, think of them as hybrid entities formed by strong coupling between light and excitations in the material, like they become intertwined.
Okay.
It's a bit like mixing two musical notes that are close in pitch. They don't just play separately, they create new, combined frequencies.
Wow, I see.
Polaritons are kind of like that. A merging of the terahertz photons and excitations within the material, specifically magnons from the iron ions, and also the electron paramagnetic resonance, the EPR, of the erbium ions.
Okay, so what did this anti-crossing look like?
So as the researchers changed the magnetic field strength, they saw the energy levels of these polaritons. They looked like they were going to cross each other on a graph, but then they veered away.
Ah, they repel each other.
Kind of, yeah. Creating this characteristic anti-crossing pattern in their frequency spectrum. Uh, Figures S2 and S3 in the supplementary materials show this really clearly. You can see these energy gaps opening up as the interaction gets stronger.
And that pattern, that's the fingerprint.
It's a spectroscopic fingerprint, exactly. A clear sign of strong hybridization, strong coupling between, specifically, the Fa3 plus Kia FM mode.
That's a type of magnon from the iron.
Right, involving the iron ions and the ER3 plus EPR mode related to the erbium ions.
And this hybridization, this strong coupling, that's the essential ingredient for the phase transition they
Yep,
saw.
absolutely. That's the driver.
Yeah.
The researchers point to a specific interaction term in their equations related to something they call dx or sometimes g. That's the driving force behind this hybridization.
Okay.
This interaction between the iron magnons and the erbium spins is what ultimately leads to the observed phase transition, a shift in the material's magnetic state, which they identify as A2 going to 12.
And how do they probe this? What techniques?
They use something called terahertz time domain magnetospectroscopy, and they did it in different setups, Voigt and Faraday geometries, they're called.
Fancy names.
Yeah, but basically these techniques let them see how the material absorbs and transmits the terahertz radiation under different magnetic fields. It reveals the energy levels of these coupled excitations, showing that anti-crossing.
Okay, so the anti-crossing shows the strong interaction. What else supports the idea that a superradiant phase transition is happening?
Good question. They also looked very carefully at how the material absorbs terahertz radiation as they changed its temperature.
Ah, temperature dependence.
Exactly. In figure S6A of the supplementary info, you can see this really noticeable kink, like a sharp change in the slope in the absorption spectra of that F3 plus QA-FM magnon mode.
A kink.
Where?
Right around 4 Kelvin. It's pretty cold. The researchers identify this kink as marking the boundary of the superradiant phase, at least when there's no magnetic field applied.
So below 4K, things change. Yes. Below this temperature, they observed that the Fe3 plus order parameter, which is basically a measure of how ordered the iron spins are, it becomes non-zero.
Meaning they line up more?
It indicates a transition into a magnetically ordered state, yeah. And that state is associated with the superradiant phase. It's like the material crosses a threshold, and suddenly this collective magnetic behavior just emerges.
Okay, so the anti-crossing shows the interaction. The kink shows the transition temperature. Now, the name also mentioned finite detuning. What's that about?
Right, that's a really important point. Remember we said the original Dicke model often assumes zero detuning, that perfect energy match?
Yeah.
Well, in this real material, erbium orthoferrate, the frequencies of the things interacting the magnons and the erbium spins, they aren't exactly identical.
Ah, so not perfectly tuned instruments this time.
Exactly. There's a slight mismatch. That's what we mean by finite detuning. And what's really fascinating is that they investigated how this detuning affects the superradiant phase transition.
And what did they find? Does the mismatch ruin it?
Actually, no. That's what's cool. Figure S1 in the supplementary material gives us the clues here. It shows that even with detuning, the superradiant phase transition can still happen.
Okay.
But the boundary defining when it happens, that shifts. It depends on how strong the coupling is between the magnons and the erbium spins. They represent this with a normalized coupling strength, Jua.
So the coupling strength matters even more with detuning.
It seems so. What's interesting is, even if the anti-crossing itself still happens technically at zero detuning, meaning they interact strongest when their energies are closest for weaker coupling strength, like what they actually observe in ERDO3,
Yeah.
the SRPT can still be reached if the ratio SO, which relates to the amount of detuning, is small enough.
So even with a slight energy difference, if the interaction is strong enough, it can still pull the system into that collective state.
Exactly. It can overcome the mismatch, basically. This robustness, even with imperfections like detuning, is pretty significant. Perfect energy matching is rare in real systems.
That makes sense. Makes it potentially more applicable.
Right.
Okay, that's really interesting. So this magnonic superradiance seems a bit more forgiving in the ideal case. Now, the paper also claims this magnonic SRPT is equivalent to the conventional Dicke SRPT, even though one involves magnons, the other photons. How do they make that connection? It's not like light pulses are coming out.
Right, that's a really crucial part of their argument. It's a cornerstone, really, and they detail it in section S4 of the supplement. They emphasize that one specific interaction, the X component of the antisymmetric exchange interaction between the iron and erbium ions.
Okay, the Dicke's term again?
That's the one,
Yeah.
the X. They argue it plays the most critical role in setting up this Dicke-type interaction. They even show that if you mathematically turn off all the other interaction terms in their more complicated model for FeO3,
Yeah.
what's left closely resembles the simple Dicke model interactions.
So this Dicke's interaction acts like a bridge, linking the magnetics to the original light matter model.
Precisely. That's a good way to put it. And to really solidify this equivalence, they use a clever mathematical trick with something called an interpolation parameter, lambda. Figure S4 illustrates this.
Okay, what does lambda do?
It basically lets them smoothly, continuously transition between their complex model for FeO3 and the basic, simple Dicke model.
Sort of dial between them.
Exactly. And what they find is that the different phases of the system, the normal state, the ordered state, and crucially the superradiant phase transition itself, they all evolve continuously between the two models as they change lambda.
No sudden jumps or breaks.
No. This smooth connection, what they call adiabatic connection, strongly suggests the underlying physics driving the transition is fundamentally the same in both systems, even though the players' photons versus magnons are different.
That's a pretty convincing argument. So different physical things carrying the energy, but the basic rules for the collective behavior for the transition, they're the same as Dicke's original idea.
That's the core argument. It's like different instruments playing the same fundamental melody.
I like that analogy.
They also looked into the impact of other interactions present in the real material. Things that aren't in the simplest Dicke model, they call them non-Dicke terms.
Okay, what do those extra terms do?
Figure S5 shows that while these extra bits can tweak the details, like maybe shift the exact magnetic field where the SRPT happens, or make the superradiant phase slightly more or less stable, they don't fundamentally change the overall picture. The qualitative features of the spectrum, the existence of the phase transition itself, those remain.
So they add some flavor but don't change the main dish.
Pretty much. For instance, they found that direct interaction between erbium ions, Ju, and another term, Xer, tend to enhance the superradiant phase, make it easier to achieve, while other terms like J, D, and Azer tend to weaken it or suppress it. So the basic Dicke recipe is there, but these extra ingredients in the real material add their own subtle nuances.
Fascinating how those seemingly small details in the interactions can adjust the overall behavior. Okay, so we've looked at the evidence, the connection to Dicke. What are the broader implications here? Why should we care about magnons acting like synchronized atoms?
Well, stepping back, this research is a pretty significant contribution to a field that's growing fast, quantum magnonics.
Quantum magnonics, using magnons for quantum stuff.
Essentially, yeah. Exploring the use of these quantum waves of magnetism magnons to carry and process quantum information. Imagine using magnetic excitations instead of, say, electrons in future quantum computers. Observing phenomena like Dicke's superradiance in these magnetic systems, it just opens up entirely new ways to potentially manipulate and control these quantum magnetic excitations.
And the fact it works with detuning helps there.
Definitely makes it more promising for potential real-world applications.
So this could be like a fundamental building block, a step towards future magnetic quantum devices.
It could absolutely be. The researchers also point out these systems are great platforms for just fundamentally studying how light and matter interact at the quantum level, but inside a solid material.
Like a test bed.
Exactly. By having a system where these collective magnetic things show such strong interactions with electromagnetic waves, we can get deeper insights into light-matter coupling in condensed matter physics. And just seeing a clear quantum phenomenon like superradiance in a macroscopic solid, it's inherently exciting, pushes the boundaries.
Yeah, it really does bridge scales. And the material itself, erbium orthoferrite. You mentioned it was complex.
It is indeed. The researchers note that to really model its magnetic behavior accurately, you need a two-sublattice model.
Two sublattices.
Yeah, one for the iron ions, one for the erbium ions, because they behave differently magnetically within the crystal structure. And this complexity leads to 4 different main modes of magnetic excitation. There are QFM and QAFM modes from the iron spins, and then in-phase and out-of-phase EPR modes from the erbium spins. Figure S2 shows these.
4 different kinds of ripples, basically.
Kind of, yeah. And interestingly, their analysis shows it's the lowest energy one, the out-of-phase EPR mode of the erbium ions, that couples most strongly to the iron's QAFM mode.
And that's the pair driving the whole Dicke-like behavior.
That's what seems to be driving it, yes. They even managed to observe both the in-phase and out-of-phase erbium EPR modes and track how their frequencies change with temperature that's in figure S7. It gives a really detailed picture of the system's dynamics.
Wow.
It really is like this carefully choreographed quantum dance happening inside this, seemingly ordinary solid material.
It's incredible to think about that level of complexity and coordination just happening down there at the atomic scale.
Hmm.
And being able to see it and understand it, that could really change things.
For fundamental understanding, and maybe for future tech, absolutely.
Precisely.
Okay, let's try and wrap this up. We've taken a deep dive into this really captivating observation, a magnonic Dicke superradiant phase transition in erbium or the ferrate.
Right. We've learned how magnons, these collective magnetic waves, can act cooperatively. Sort of like a synchronized choir, but with magnetism instead of sound or light.
Like that superradiant burst. And we've hit the key evidence that anti-crossing pattern in the polariton frequencies, the kink in the absorption spectrum telling us the transition temperature. And we explored the crucial links back to the classic Dicke model, even with real-world imperfections like finite detuning, highlighting how specific interactions like that Dapex term make it all work.
And it still feels pretty mind-boggling witnessing this fundamentally quantum-like collective behavior in a tangible, solid material, something you could, actually hold.
It really is. It's a testament to these deep connections between the quantum world and the macroscopic world we experience.
Yeah.
Which brings us maybe to a final thought for you, our listener, to ponder. Consider the implications if we can truly understand and then control these collective magnetic excitations with precision. How might that knowledge lead to entirely new ways of thinking about material science, or maybe enable completely new kinds of quantum technologies?
What else could be hiding in plain sight?
Exactly. What other unexpected quantum behaviors might be lurking inside seemingly conventional materials, just waiting for us to find them? It's a really exciting time for exploring light-matter interactions in solids, and quantum magnonics. Definitely a field to keep an eye on.